Hi, welcome back to my channel. This is the second in a series on the history of the LISP programming language from Lisp all the way to Racket. Today in part one, we discussed the rise of Lisp. And if you haven't seen that video, please go back and visit that. In this video, we're going to take a look at Scheme, which was invented at MIT during the 1970s as part of a course called Structure and Interpretation of Computer Programs, which also had a textbook specifically written for it. And it's fairly well regarded in a lot of circles as being one of the best texts in computer science in general. So what Scheme did, what are the changes in addition that it added to Lisp? And there's quite a few interesting ones. One is that if you remember in part one of our series, we talked about how Lisp was dynamically scoped. Scheme changed that to make it lexically scoped. So to follow that it turns out much more of the programming languages were using lexical scope at the time. And it's something that they found that, of course, made more sense than dynamic scoping. And also, while it was a little bit more complex to implement, it greatly simplifies what you could do with the language. And while it took away the magic that could happen with Lisp in terms of how you extend it and provide extensibility because you have dynamic scoping, that was found to be better. They wanted to actually try to simplify things so that it was a little bit easier for students to understand and follow what the programs were doing. What they also brought in is that they brought in the notion of what's called tail-called optimization. We'll discuss that. Also of note, they brought in what was called first-class continuations. And as a part of this whole adding lexical scoping versus dynamic scoping, they had to modify the concepts of how macros worked to become what they called hygienic macros, which would allow you to fairly easily write macros, but still respect the lexical scope and not inadvertently capture variables in a macro. And they called those hygienic macros. Okay. So first of all, Scheme just uses the lexical scoping rules that languages use today. It removed a lot of that extensibility magic of dynamic scope, and that made the language a lot more simple in terms of thinking about what a program would do and reasoning about it. And of course, it was a little bit more complicated to do lexical scope, but by this time, computers were getting fast enough that the optimizations that dynamic scope allowed weren't really as necessary as basically there's a little bit more smarts about how they would compile to things and how you could look up variables in lexical scoping would be done a little bit more efficiently. So that was also driving that as well. So the second thing they added was basically something called call optimization. And this is kind of served by an example. So I'm going to break out a little bit of Scheme here. So what we have is we have a function here, and all its purpose in life is just basically it's to sum up the values from 1 to n. And the way I do this is I define this recursively. I go off and say, hey, obviously if n is 0, then that's 0. That's great. Otherwise, we add n to the sum of n minus 1. And so this is a recursive definition. The thing about it is interesting is that if we take a look at it, the recursive call, or the call to the function itself, is the last thing that is being done, or is what we call a tail position. And this is the interesting thing about this is that because it's in tail position, the compiler can do a very interesting optimization. And what it can do is that what Scheme will do and other languages that do tail call optimization, and there's quite a few of them out there that aren't even functional. For example, C# will do tail call optimizations. Newer versions of Java, I believe, even will do tail call optimization, as will, I think, most C++ compilers do as well. So what this does is that it does not actually turn this into a recursive function call. It actually transforms that entire code into a loop. And so that ends up being exactly like the loop that we expect that goes from, zero, n to 0 and does all the checks. So it actually makes recursive calls. This optimization is why Scheme is actually, and later versions of Lisp that also took this on, Common Lisp adopted this later on as well, is that's why it's actually fairly efficient where you don't have a looping construct. And the reason being is because it can use this thing that take these simple recursive calls and just turn them into loops and do that very efficiently. And so while there are still loops in Scheme, there is ways to do what's called the for loop. Just a lot of cases, people just use tail call based recursion and use tail call optimization to take care of it, because ultimately it will turn it into a loop that's just as effective as writing a for loop. So that was a very, very clever thing that actually really added to the usability of the language in terms of its functionality in a larger set of programs. The next one is I bring it up because it's very important. It has led to a lot of very interesting research in computing, and it kind of laid the ground for some of the modern features that we use today. And basically, but again, it's a really complicated type of thing. But basically, it allows for you to explicitly kind of manage complex control flow without having to have explicit keywords and compiler support and runtime support. Well, you have to have excuse me, you have to have some runtime support. Obviously, you have to have support for continuation itself, but you don't need to have things like specific keywords necessarily or specific types of this explicit control flow with its own keywords and everything like that. You can use this to implement all this kind of stuff. And what it can be done is that you can do things like exceptions, try, catch, finally. You can do things like generators and in JavaScript or C#, where you lazily add out values. You can use them to do coroutines. If you tie into a thread library, you can use async await to do this. Even though in like C#, the original language that did this, it does it in a slightly different way than by using continuations. But the idea is the same, that ultimately all these complex control flows can be done as a notion in terms of doing continuations. Not only that, but there's some very advanced work done by Andrew Appel on how communication-based style for in compiling can be used to compile very complex functional languages in a very efficient type of way. And some of that stuff actually did make its way into things like LLVM in terms of how they treat their intermediate languages and stuff like that. So again, the very complex stuff, like gradual level topics, don't necessarily get into and stuff like that here because it would basically take forever. And it's something that very few programmers might use, but it is there as a powerful way of extending the language. So again, hygienic macros. When you're using lexicoscope, making macros becomes a lot more challenging. And the reason being is that you have to be careful about how you name things. And ultimately, regardless of how careful you are about naming things, you need the macro system to go off and make sure that it never, ever, ever will capture a variable. And so the hygienic macros did that. They basically go off and say, oh, we'll make sure that we have completely unique variable names and symbols and stuff like that, and that things will not collide, and you capture things in the environment intentionally, not unintentionally. And basically what it comes down to is that in programming language theory, we talk about the notion of a free and bound variable. A free variable is something in which it does not have a value yet. And a bound variable is something that has been given a value. And when variables are free or bound is a very important part of determining how you interpret a programming language as well as compile it. So there's a lot of work about how that's done. And hygienic macros make sure that it does the right thing, quote unquote. And so ensuring this actually required a lot of clever work underneath the engine itself, but they didn't want to necessarily expose that to end users and have them take on the burden of doing it. So that was why it was fairly interesting. And macro hygiene was something that Common Lisp also took a look at, and there's some dialogues that actually try to move towards more hygienic macros by default. There's others that don't. So the whole point behind Scheme was it was meant to be used in teaching. It was really developed alongside this textbook called The Structure of Interpretation of Computer Programs. It started out as a research project, but really ended up being primarily this was its first and main use and most popular use was being taught in this class. And for a long time, it's a required course at MIT. It's still an elective, but it's no longer required. And now there is a JavaScript version based on the second version. I will say that the JavaScript version seems like, oh, hey, it's JavaScript. It'd be much more interesting. I'd really recommend that you use the Scheme version. There's certain things about the Scheme version where there's less workarounds. There's less, to be perfectly honest, cruft in the JavaScript version. And so unless you're like really, really, really tied to the fact that you want to do everything in JavaScript, I would definitely say if you're interested in this book, take a look at the textbook in the Scheme version. And the thing about it is that it is freely available. You can buy copies of it, of course, if you want to have something on your shelf. But there's a website for it that there's a HTML version, there's a PDF version that's easily and readily available for you to use and free of charge. So the reason I bring this up is that for me, a lot of people talk about like big textbooks and big books in the course of computer science, and the one that brings up a lot of people bring up is like The Art of Programming. And while certainly that is an amazing accomplishment and something that if you've gotten through and understand, is really noteworthy. But I would say, in terms of effort, you would get more out of learning and studying the SIP textbook than you would being the art of programming. The art of programming is an excellent overview of algorithms, but I think it's much more of a reference text in that regard, and capturing really, it's basically capturing what will be like this large set of algorithms that people can draw on for many years to come. And in that sense, it is almost a book itself that is historical, in that it captures kind of this historical evolution of what we understand from algorithms and what we demand from them. That being said, the amount of algorithm development that most people do is vastly smaller than trying to deal with how to best use a language and optimize the language features and reason about it. And the art of programming, by definition, does not cover that. It really is about algorithms and data structures. And structure and interpretation of computer programs is basically about that. How do you interpret and really understand what a computer program is doing? And the thing about this is that the other thing about it is that by learning scheme and having things stripped down in terms of syntax and semantics, you really kind of understand the essence of a programming language, and you start to see all programming languages as dialects in a certain family of languages. And it makes it a lot easier for you to understand and adapt to new languages, which increasingly it was always an important skill, but now has really become a very interesting skill for a lot of projects. They are using more than one language by default. And not only that, but there's certain languages that are coming online that people are finding more and more useful, and being able to adapt those quickly is a great type of boon. So, and in your career, it'll be great to be able to move from one thing to another and say, hey, I'm not just this programmer, but I'm a programmer who uses these languages. So the material can seem fairly abstract in SICP, but if you engage with it, there's really a lot of great stuff there. For example, its introduction to issues around concurrency and modularity are really, really good. I can't stress that section enough. It really helps you understand concurrency in a way that isn't tied to just how operating systems work and how threads work. So as part of this, there's some standardization around this. They created a report on Scheme, and then they revised it. And this turned out to be the naming conventions for the language is very weird. So if you talk about R7RS, that is the 7th revision of the Scheme language standard, and R6RS would be the 6th. So very odd way of doing things, just kind of to be very clever. Not only that, but some people would know, well, that's not even the right way to do this, because it shouldn't be the 7 to 6 should be a superscript, not just a regular number there. So again, maybe a little bit too clever for its own good, but once you see it, you're fine. So I just bring that up so that when you look at things, and when people talk about Scheme, they often talk about R5RS versus R6RS versus R7RS. And, that's just good to be aware of if you're taking a look at some of these things and doing some more of your own research. The thing about it is that there's some things that happened that were very interesting when they went from the R5RS to R6RS. R5R6 was a fairly small text that defined a fairly small language, but increasingly wasn't capturing what was going on in the larger Scheme ecosystem as it was at the time. So R6RS addressed this, but the complexity of the standard grew by quite a bit. A notable amount. It more than doubled. In some cases, you can say about tripled in terms of the amount of text that's being able there. And not only that, but the density of the text really increased as well. The development of R6RS really kind of led to a lot of internal frictions within the community, which wasn't very large, but was also very passionate and very bright. Part of what came out of this was the following. One of the implementations of Scheme that was getting a lot of traction used in education was called PLT Scheme. And it had a set of tools that was being used in a lot of courses. One of those tools was a thing called Dr. Scheme, which was its own IDE that was invented to be a way of helping students kind of first learn programming. And it was kind of in the vein of how Smalltalk had its own development environment built in, trying to address that, and making things more interactive, coming up with language dialects that would make it easier to do things. So a lot of tools that oriented around teaching. And this was when IDEs were very much either you were using a text editor or you had basically had to pay a lot of money for a commercial IDE like Visual Studio, and even JetBrains wasn't really a thing back then when they first started this. But anyway, during post R6 RS, they kind of looked at this and looked where they were going, and the PLT group decided that it was best for them if they really went on and they did their own work the way they wanted to do it and go their own way with the language. And to do so, they decided that the first thing that they needed to do was rename the language that they're developing, so that there wasn't any confusion with other versions of Scheme, because they wanted to know that this was a fork in the road and there could be potential incompatibilities, and they didn't want to add additional confusion. So they named it Racket because Racket is a synonym of Scheme. So that's why it's now called Dr. Racket, and while it's PLT Racket is the language. So Racket differences. They really added in this notion of what's called the lane construct, which is basically this kind of at the very top. It has this notion of you can choose language dialects, and there's lots of them, and that Scheme didn't have that concept. And basically what the lane construct does is a lot of things in terms about what libraries are loaded in by default, what the syntax is going to be, and it makes it so it's really flexible and interesting. And so that was something that they added in that was going to be, that is new from Scheme. There's also changes about mutable lists. You do have mutable lists, but they're not necessarily the default. You have to use them explicitly. The thing that they also added in is that they added a module system, so that you can do things like basically everything kind of lives in a module, and you can explicitly provide and require things from modules. And so they did the hiding there, and that actually made it a lot easier for people to develop libraries because not everything was like colliding in the global namespace. They did some other stuff around continuations. They added in a notion of delimited continuation and continuation marks, which added some very clever optimizations if you're doing work around continuations. They kind of upgraded the. There's some ideas about this that was being done in R5 RS and how terms macros doing in terms of syntax, and they really kind of pushed that forward into their own model and developing syntax transformers versus the older version of macros on RSR5. There's also little changes that have gone along the way that I'm sure that I've missed, but that's basically what it came down to. Not only that, but one of the things that the Planet Racket people did is that they provided basically they have a way of hosting packages, and they have a package manager in the language, and that was actually kind of new. Even with there's actually, if you look at all the other Scheme implementations, they may or may not have that. PLT Racket is one of those things where it has a built-in tool and a built-in package manager repository and a default place to publish those things. So that's a and if you're doing modern programming languages, obviously that's a very useful and important part of having a modern language. So on the other side, when it went to Scheme, they decided when they did R7 RS and working on it, they decided to split the standard into two parts. They wanted to do the small language, and then they also wanted to try to catch up and capture some of the things about it in a more standard way for what they call the large language. That work is still in progress. And given that it's 2025, you can kind of see how the landscape is changing in terms of how you develop languages. And this is where I think there's an interesting history as well. I see things as is that there's a lot of emphasis. In the first case, in the 50s and 60s, there's not a lot of formality around developing programming languages because there's so much that was happening so fast in such a small set of circumstances that there really wasn't any need to do it. But at some point, a lot of things did get standardized, Fortran, COBOL, and these were highly structured processes, and they also targeted multiple implementations. C++ is an example, Fortran 77 versus Fortran 90 is an example. You have ECMA script, and early versions of C# was like that. Java, I wouldn't say Java is different, and I'll get to that, because it was a highly structured process. Now, kind of very structured, where you want to make a standard, but it's really targeting a single reference implementation. Java and the early C# was like that. And now what's happened is that the process is much less structured, depending on certain types of things. And it's much more not about a documented standard or semantics, but it's much more around not only just a reference implementation, but reference code. And I think things like TypeScript, Modern C# is just like this. They haven't really updated the standard, the ECMA standard that they had for quite some time, because there's not really demand for it, because the language is what it is, and the way they implement and track new features is all through GitHub and a much more decentralized. There's a decentralized and democratic process. They have a benevolent dictator that ultimately decides what goes in. But ultimately, if you want to make changes to languages and you champion it and you get enough code in there, you might get your changes in. And what it is that the other languages that are in this kind of older model are really kind of suffering. If you take a look at C++, for example, how it evolves features can take a very, very long time compared to how Rust develops things, because they're a much less structured process, and they're targeting a reference implementation, and they're just borrowing things in kind of an open source manner. So to sum up here, Lisp looked like it was going to be the language of choice in the 70s. And there's a lot of great work being done about it. Like I said, there's people building specific hardware even to try to target and make Lisp run faster. But it didn't happen. And again, if you take a look at part one, it's really that C# and Linux and no, excuse me, C# and Unix, then Linux and other types of languages in that kind of whole dialect really came to prominence, really took off, and kind of undermined a lot of not undermined, but basically just overtook what Lisp was doing in terms of performance and being able to do things. And when C++ came along and early object-oriented programming came along, that really exploded the amount of coding that people were doing. And that's really where that kind of cemented that kind of object-oriented dialect as the way that people wanted to do things. That is actually kind of changed now. There are more people that are interested in functional programming languages. The weird thing about that is that the interest in functional programming languages is coming from a completely different dialect of languages that people call the ML family of programming languages. ML stands for meta language. It was an idea invented at AT&T to kind of basically use a different syntax, but to explore different ideas in functional programming that didn't really tie into Lisp. And so it has its own function, it has its own syntax, but it inspired a whole set of languages after that. The first one was kind of OCaml, which added object-oriented concepts to ML and did some new features. And then you had Haskell, which really brought in and formalized things about, being lazy as possible, really doing monadic structure, basically monads really is a first class type of thing that people really understood in terms of dealing with state and IO and all those other types of things, which has led to, if you're aware of this, people vastly wondering why they had to use this bit of category theory, and other people saying how awesome and incredible it is that they're using this bit of category theory. So a lot of people are interested in Haskell. Of course, there's a lot of people noted, not as nearly as many people using Haskell in the real world than are interested in it. And certainly past that, there's things like in the formal verification community, there's languages like COQ, COQ, excuse me. That was a French language, kind of also in that vein. And then now Agda, and both those languages I talked about there are really used for theorem proving and developing things around dependent types. So its successors, Scheme and Racket, did have this early impact on how programming languages were taught. The structure and interpretation of computer programs, that textbook was used a lot back in the 80s and coming up to the 90s. It has been displaced. And as a personal commentary, I will say displaced was probably to the detriment overall of education. There's a lot of places that don't even have it as an option now for studying as an undergraduate or graduate. And that really leads to a big gap in people understanding programming languages. And the reason being is that it's not always the best thing to use something that is really practical and used all the time, because those languages sometimes have compromises in them. And it's sometimes better to understand something that was very specifically designed for a certain specific set of tasks, even though it wasn't necessarily meant to be used in all these big production types of stuff. That being said, I will say Racket is not something where you're not going to be able to do anything. They have plenty of useful programming packages. So if you wanted to do things like, use a web server or make a web client or even make a web server, they have packages to help you do that. So it's not like they live completely devoid or in this void of anything useful. It's just that it is not necessarily going to the point where it's like it wants to be the programming languages that everybody out in the world programs in, and versus being able to be something that allows people to really understand the fundamentals of programming languages themselves. So if you've gotten this far, thanks for watching, and please like and subscribe. This is some bonus content that I'll go into that is completely optional. And it's just basically some background of why I looked at why I use Racket and I'm doing videos on it, as well as some things I'd like to see from Racket. So feel free to stop here. But if you're interested, please continue on, and I appreciate it. So why have I made a bunch of videos on the Racket on Racket programming language? And certainly look at them. There's not a lot of people that they don't get a ton of views compared to some of my other videos. But first of all, one of the main contributors to the language, Matthew Flatt, was at the University of Utah where I studied. He was on my PhD community and was very helpful and useful in that regard. And I took some classes from him, and he's a really great educator and a really great person to work with. And the interesting thing about it is that you can see this kind of thing where Racket was kind of this great example of how developing languages by hashing out a reference implementation seems to be the future of language development. And that's what's been really interesting to me. And that's why I kind of want to bring people and have some more familiarity with it. So they can kind of look at this and kind of say, oh, hey, this is this interesting place. And not only that, but since they have a smaller group, it's a place that where if you got in, if you got in and became really interested and wanted to make some contributions, it'd be an excellent community to help do that in. And so if you're really interested in this kind of topic and want to do things like, hey, make some contributions, there's the Racket community might be an excellent place to do that. So, and I'm certainly trying to consider how much time I can give to doing some open source implementation stuff. Again, for personal reasons, I have a limited amount of resources in terms of how much time I can dedicate to certain types of those efforts. The second thing is I really do miss teaching. I got a PhD not so much to be a researcher, but to be an academic teacher. I loved teaching classes when I was working on my PhD. And I still feel that for everybody that wants to really, juniors or even some seniors or mid-level senior programmers who want to become better at programming, and if they haven't engaged with the ideas behind in Scheme and the whole how to design program textbooks and the structure and interpretation of computer programming textbooks, that is some of the best ways you're going to become a better programmer, because you'll open up a whole new world of being able to shift from programming language to programming language without much of a thought. You'll be a little bit more tolerant of cruft to some point. And not only that, but ironically, in some cases, it might help you understand why TypeScript and JavaScript is the way it is, because it really is based on Scheme and Racket, and very poorly so, to be blunt. But it will tell you, kind of give you an idea of how to think about, oh, well, this is why it does certain types of things. What would I like from Racket if I could wave my magic wand right now is I would like them to basically build up more of the language server protocol support and also add the debug adapters protocol support. And this is all around making Visual Code a first-class experience. And modernize Dr. Racket. So, basically they have to, it's kind of using an older version of GDK. You can kind of tell it's got a lot of rough edges on it, really modernize it. There's a case that I can be made that you could go whole hog and just actually make Visual Studio the default target for making the first class experience. And I think that actually would be very good because I think it would bring even more people into there and provide even less resistance to using it as a language if people would be using VS Code for it. And I actually might talk to some people in the Racket team and seeing how to move forward on that to make that possible. And lastly would be to compile not only down to they have a version of Scheme that they've adopted that actually does compile to native language and it does very well, but to add WASM support to that stack. And so that would be really awesome. And again, like I said, if you're interested in this kind of stuff, there is really no better place to put all the stuff in than basically in terms of being able to work with the community, get in there and make some impact. The Racket community is one of the best you can do. And if you're looking to build that resume up, even being able to make small contributions to that code base would be pretty interesting. So I would again encourage you that if you are really interested in this kind of stuff, engage with that community. They have a discourse, they have GitHub, all that kind of stuff, and they're good people there. So, all right, if you made it this far, again, thanks so much, and like and subscribe.